Hi everyone, I'm Perlyn and I'll be sharing about my FYP on provenance graph generation for intrusion detection. I'll start off with an introduction to the project, followed by methodology, results, conclusion, and future extensions. With the rise in digitalization, our critical infrastructure has become increasingly vulnerable to potential cybersecurity breaches, and there is an urgent need to develop methods to safeguard our systems. Intrusion detection systems monitor both inbound and outbound traffic for any anomalies and act as a first line of defense against cyber threats. However, traditional intrusion detection systems are increasingly limited and are unable to identify malware signatures of new attack vectors like zero-day attacks or advanced persistent threats. Hence, modern approaches are required to tackle the new and increasingly complex cyber attacks. Provenance is generally defined as a record that describes how entities, activities, and agents have influenced a piece of data. And in intrusion detection, provenance represents the dependency relationship between the damaged files and the intrusion processes. It reduces false alarms by recording the data flows between files and processes instead of system call sequences, and can output the system vulnerabilities and sources of intrusion in real time. Provenance graphs have been well recognized as a useful element for defending against intrusions. However, historically, there have been a lack of pipelines for automatically generating provenance data from cyber attacks, capturing the provenance data, then generating provenance graphs suitable for machine learning. Hence, the Flurry framework was created to tackle the need for usable graph representations for machine learning tasks. In this project, the goal is to improve the generation of provenance graphs as the data source for intrusion detection. To do that, I designed intrusion scenarios and simulated attacks on multiple security-sensitive applications to generate provenance data. Next, I validated state-of-the-art graph-based models with extensive provenance graph datasets. Now onto the methodology. There are 4 main sections. First, I identified 7 key attacks and designed intrusion scenarios for them. Next, I first did some exploration on Fedora, the recommended OS, then implemented Flurry on Ubuntu. Lastly, I generated large provenance graph datasets and trained a graph neural network. Included on the right is the system architecture, which includes the automated execution and provenance generation using the then vulnerable web application, and then provenance capture using CamFlow, then MQTT for message queue service, and next the Flurry framework to create the provenance graphs, and lastly a graph convolution network to perform graph classification. First, prevalent attacks were selected and identified based on the top security risk identified by Hackmageddon and the OWASP. Next, exploration on Fedora was performed to better understand CamFlow and Flurry. The bulk of the project was implementing on Ubuntu. Previously, CamFlow and Flurry were mainly supported and tested on Fedora. However, Ubuntu is a much more popular platform, and we need to evaluate the capabilities and performance of CamFlow and Flurry on a contemporary and widely adopted Linux distribution. Since Ubuntu was not supported and the codebase was largely incomplete, the first step was to build an easy-to-install codebase. Hence, I wrote multiple scripts, including a shell script to install all required dependencies such as CamFlow, XAMPP, then vulnerable web application, Mosquito MQTT, and configure all these services. Additionally, I also wrote shell scripts to run the program and all the required dependencies, as well as attack scripts to dynamically run attacks. The following is the demo of the program automatically running an attack. Lastly, a graph neural network, and specifically a graph convolution network, was implemented and validated with the provenance graphs. For this, I first generated 2000 benign and 2000 malicious provenance graphs for each attack type. Next, I performed data processing using one-hot encoding into a deep graph library dataset. Then I trained the model with cross-entropy loss as the loss function, and then performed hyperparameter tuning. Lastly, with the most optimal model, I trained the model across all the different attacks. I first varied batch size, which is a trade-off between accuracy and training duration, with batch size of 1 being more accurate but taking longer to train. Next, for hyperparameter tuning, I varied the number of layers and the size of the hidden dimension. And through my experiments, I found that a 3-layer GCN with size of hidden layer 256 performs the best. Hence, I performed graph classification using a 3-layer GCN on 4000 samples for each attack with batch size of 1 for 50 epochs and obtained the following results. Overall, the model achieved an accuracy of around 82% across 6 attacks, with each attack being trained using 3 seeds. The model performs well and classifies provenance graphs accurately to detect attacks. However, accuracy and false alarm rate vary across vectors, attack vectors, depending on how different the system execution of the attack is from that of the benign scenario. And through the experiments, provenance graphs have shown to be effective in intrusion detection and allows state-of-the-art graph models to easily learn and detect threats. Summarization images of graphs for visualization are also generated as follows. And in conclusion, Flurry provides an effective and efficient framework for the automated generation of provenance graphs and streamlines the entire process. From the data generated with Flurry and trained with a graph convolution network, the strong performance of state-of-the-art graph-based models and graph classification exemplifies the potential of provenance graphs as an ideal data source for modern intrusion detection systems. Lastly, for future extensions, efficacy on other Linux distributions like the Red Hat Enterprise Linux can be tested, as both CanFlow and Flurry have great potential in commercial settings. Next, we should also increase the diversity of provenance graphs and generate more complicated and dissimilar provenance graphs. Lastly, to improve on machine learning implementation such that the model can be able to classify across attack types such as malicious and benign, and ultimately even classify the attack type. Thank you.